You're ready? No technology? Chuck?
Chuck's a technology.
Is it properly erased? Is the blackboard properly? So, Cary Malkiewich will talk about periodic points and topological restriction homology.
Thank you so much. And thanks for the invitation. And thank you, everyone who's here, for showing up at the crack of 9 for this talk. So I'm going to talk today about a project with Kate Ponto. And overall, what this project is about is a bridge that connects dynamics, or certain parts of dynamics, to trace methods in algebraic K-theory. And the rough idea is that fixed point theory is governed by THH. And then there's a corresponding generalization that says that periodic points should be governed by TR, topological restriction homology. So I know at this conference there's a lot of diversity in the crowd, and so if you really like THH and TR, great. And if you're less comfortable with them, anytime I say THH, I mean, what I'm really thinking about is free loop spaces. So you can feel free to just substitute that in whenever I talk about THH. And when I talk about TR, well, it's a little bit harder to say what to substitute in, but at the very least, you should be thinking about the fact that a free loop space has this action by the cyclic group that rotates the loops around. And so TR is something to do with that. Okay, so I'd like to explain this bridge a little bit. And I want to start at the beginning with fixed point theory. So the kind of fixed point theory I'm going to talk about is also called Nielsen theory. So let's suppose that M is a compact manifold of dimension at least 3. A lot of what I'm about to say actually doesn't need these assumptions, but there's at least one thing that does. And suppose that F is a self-map, continuous. Then the question that I want to talk about is, does F have fixed points? And even if it does, can those fixed points be removed? So the question is, can we remove the fixed points of F by a homotopy? If you like, this is a question about homotopy invariant properties of this dynamical system. That's a very classical question. Here's a very classical answer. Well, a partial answer. So if F is homotopic to something that's fixed point free, that's my abbreviation for that, then the Lefschetz number of F has to be 0. Probably most or all of us are familiar with that. But I'll just remind you about what the Lefschetz number is. The Lefschetz number can be defined 2 ways. One is it's an alternating sum of the trace of the action of F on the homology groups of M with rational coefficients. So that's a vector space. F acts on the vector space that has a trace. I take the alternating sum of the traces. The second definition is a sum over the fixed points of these integers that are called the index of that fixed point. So the second definition is that it's a weighted sum of fixed points. Of course, it's a non-trivial theorem that these are equal. That's the Lefschetz-Hopf theorem. And that's the theorem that implies this. Because if I can remove the fixed points, then that's an empty sum, hence the Lefschetz number is 0. So in other words, the Lefschetz number is an obstruction to removing the fixed points. Now, I said at the beginning of the talk that fixed point theory is governed by THH. So what does this have to do with THH? Well, nothing. But this isn't the end of the story, because that's a one-way implication. So how do we go the other way? If the Lefschetz number is 0, then how do we remove the fixed points? So it turns out you almost kind of can remove the fixed points, but there's a problem that might come up. So say I have two fixed points, x and y. The problem is it possible to deform f by a homotopy that joins those fixed points together? So if you think about it, if I could always do this, then I could bring all the fixed points together. And if the sum of the indices is 0, then you could argue locally I could remove those fixed points. So the only issue is turning it from a global problem into a local problem. How do I bring all these fixed points close together? And if you think about it, well, probably you need a path in order to do this. If you don't have a path, then I can't imagine how to bring them together. If you think about it a little more, when I apply f to that path, there's f of the path. I'm going to want a homotopy between gamma and f of gamma. So once you have that data, you can imagine modifying f near this path so that instead of sending gamma to f of gamma, it sends gamma to itself. And then you can join those fixed points together. So this puts an equivalence relation on the fixed points. I say that x is equivalent to y if I can draw a picture like this. And it's not always the case that two fixed points are equivalent. So this sorts them into classes. Sorts the fixed points into classes, or into bins. Okay, so what does this have to do with free loop spaces? So here's a way of reinterpreting these bins. So define lambda f of m to be the homotopy equalizer of the identity in f. In other words, the space of choices of point x and then path connecting x to f of x. I'm going to call that, going to move this up a little bit. I'm going to call that the twisted free loop space. If f is the identity, then this is exactly the free loop space. So now, let's make a couple of observations about the twisted free loop space. So first observation, what are the constant loops? The constant loops aren't m. Oops. Getting dramatic with my chalk. The constant loops aren't m. The constant loops are the fixed points. In other words, the strict equalizer of the identity in f. The other observation, which is only slightly harder, is that two fixed points are equivalent, in this sense above, if and only if they lie in the same component of the twisted free loop space. So you can prove this just by staring at the pictures that I've already drawn. This picture here is a one-parameter family of pictures like this that go from a constant path to a constant path. So that's the argument. So these bins that I want to sort the fixed points into, the bins are just the connected components of the space.
Now we're saying this space is just the homotopy fixed points of f x.
That's right. That's right. This is the homotopy fixed points of f. So the actual fixed points are contained inside, and the bins that I want to sort the actual fixed points into should be the components of the homotopy fixed point space. So that gives us an invariant that is classically called the Reidemeister trace. It's spelled with a D. So this is an element of the zeroth homology of the twisted free loop space. Or if you like, the zeroth stable homotopy of the twisted free loop space, because those are isomorphic groups. And so if I think, so this is a free abelian group, but if I think of the elements as functions from the components to integers that are finitely supported, then it's the function that sends each component to the sum over fixed points that lie in that component of the indices of the fixed points. So you could alternatively describe it as, for each fixed point, I take its index times whichever component it lies in. And that's the element of homology that I get. So if you recall this argument I said earlier, essentially you want to bring the fixed points together and cancel them. If you believe that argument that says, well, if this Reidemeister trace is 0, then within each of these equivalence classes, the indices sum to 0. So within each of these equivalence classes, I can cancel the fixed points. And that's exactly what happens. This is the theorem of Ekin. This is from the 1940s. That f is homotopic to something fixed point free if and only if this Reidemeister trace is 0. This is where I'm really using the fact that I have a manifold and the dimension is at least 3. I mean, to be very rough about that, it's because when you're deforming f to bring the fixed points together, you don't want to accidentally create new fixed points. And so that requires having this surface be disjoint away from the curve, have this surface be disjoint from that curve. So that works when your dimension is at least 4. And then when your dimension is at least 3, well, they intersect 0 dimensionally, but that still turns out to be okay. And then for surfaces, it's just false. Right? So that's what fixed point theory has to do with free loop spaces. It's when you want not just a Lefschetz theorem, but a Lefschetz theorem with a converse. Right? This if and only if down here, that's when the free loop spaces show up. All right, so this isn't quite the end of the story. In some ways, this definition is unsatisfying, right? You have to know what the fixed points are before you can calculate this. So this isn't the end of the story. What you still want is a more algebraic definition, like the alternating sum of traces. You also want a more conceptual definition. Because the more conceptual the definition is, the easier it is to generalize it, solve generalizations of this fixed point problem. In particular, we'd really like to be able to have a converse Lefschetz theorem for families of fixed point problems. If I have a fiber bundle and I have a fiber-wise self-map, I'd like to know what is the complete obstruction to deforming those maps fiber-wise to remove all the fixed points. So this was explored by Geoghegan-Nikas for one-parameter families. They took some classical definitions of Reidemeister trace in sort of a straightforward way, said, okay, we'll generalize this to one-parameter families if we're parametrized over the interval. But once they did that, it wasn't so clear how to go further. Right? In some sense, you don't want to just keep making ad hoc definitions. You want to have an overarching idea of what sort of thing is the Reidemeister trace. How do I generalize it? And so these two goals are actually connected together. All right. So to talk about how to think about it, we have to talk about traces. So that's the next part. Let me begin by recalling how the trace works in a symmetric monoidal category. And for concreteness, I'm going to talk about a commutative ring. So R is a commutative ring, or a ring spectrum. And I'm going to look at modules over R. You could even let R be a field, so I'm just talking about vector spaces. So let V be a dualizable left R module. R is commutative, so you can just say R module. So of course, for a vector space, that means finite dimensional. For a ring, that means finitely generated projective. For a ring spectrum, that means a retract up to a homotopy of a finite cell spectrum. And I'll let V dual be the R linear dual. So R homs from V to R. If I'm working with chain complexes or spectra, then I want these things to be derived. So every time I take a hom or a tensor product, I'll really be taking replacements or using a bar construction. So how do I take the trace of an endomorphism F? This is a pretty familiar recipe, I think. So I start with R. I go to V dual tensor over R with V. Then I flip these around, v tensor over r with v dual. Then I apply f tensor 1, v tensor over r with v dual. And then I go to r. Okay, so what is this map? So you're supposed to think of this as n by n matrices, where precisely there's an isomorphism to r homs from v to v. And inside those homs, there's an identity element. So this is the map that's sending 1 to the identity element. In other words, these are matrices, and I'm picking out the identity matrix. Then when I go over here, I apply f. So now I have the matrix of f. And then this last step is evaluation. Plugging your vector into your linear functional, and thinking in terms of matrices, that's exactly where you take the trace in the classical sense. So, of course, when you phrase it this way, this isn't just a statement about modules over a commutative ring. This makes sense anytime you have a commutative tensor product, so in any symmetric monoidal category. So then I can just take R to be Z and take my module to be, say, cellular chains of M, or I can take R to be Q and V to be homology of M with rational coefficients. Either of those two settings, the trace is giving me the Lefschetz number. So that's how I can conceptualize the Lefschetz number. It's a trace in a symmetric monoidal category. This is what I mean by a conceptual definition, and this is the kind of definition that we also want for the Reidemeister trace. So we want something like this. Okay? Well, to do that, can you guys see if I write over here? Yeah? Okay. So to do that, let's say, well, so what if R is not commutative? So if R is not a commutative ring, let's say it's still an algebra over some commutative ring K, to what extent does this recipe still make sense? Well, if I take the dual of V and V, and I tensor them together, I still get this isomorphism. And so I still have an identity element, and so I can still define a map here. Slight complication, that map isn't a map out of R, it's a map out of K, because I lost the R action when I tensored over R. On the other side, I have V tensor V dual goes to R. That still works. I still have an evaluation map, but now it's a map out of the tensor product over K. It's not a map out of the tensor product over R. So it looks almost like I can do this, except it kind of breaks down. Since R is not commutative, I can't quite define the trace. So how do we fix this? Right. So over here, I've divided out that R action. Over here, I haven't. And so that's why I don't get a map. Well, the most straightforward way to fix it is to just divide out by the R action here. Right? I divided out by R over here. So over here, I could just say, apply the equivalence relation. I can pull off an element of R and stick it on the other side. So let me represent that by drawing a circle and writing tensor on the outside over R. If you just apply that equivalence relation, then suddenly you do get a map. In fact, it's an isomorphism. The price you pay is that then you've also tensored the outsides over here, over R, and you've also tensored R to itself. So you end up not in R, but in a certain abelianization of R. As an abelian group, you've modded out A, B is equal to BA. So that's one way of defining the trace. In fact, this generalizes. So suppose that I'm working in a derived setting. When I write a tensor product, I really mean a bar construction. When I write this, well, it's tensor product over K, so I can just take that strictly if I like. So if I'm in the derived setting, what should that mean? Well, that should exactly mean a cyclic bar construction. So I draw this picture. What I should be doing is Hochschild homology. And then I can conceptualize this even further. So this is two modules where I've tensored them over K on one side and over R on the other. Before, when I'm over here, I could imagine they're tensored over R on one side, and they're tensored over K on the other side. And then K has been tensored to itself. So if I conceptualize it that way, then everything is taking place along a circle. And when in a symmetric monoidal category, the point where I'd switch the two terms, instead of swapping them, I'll just take the circle and I'll rotate it 180 degrees. Right, so that's how we can conceptualize taking a trace when I'm over a non-commutative ring. Okay, so let me write that out. Let's see. Let's do it over here. So I'm writing this in a suggestive way. Just like the trace over here makes sense in any symmetric monoidal category, the trace over here is going to make sense in any setting where I can draw pictures like this, where I can tensor things together not just along a line, but along a circle. And if I rotate the circle, I'm getting the same tensor product. So Kate Ponto formalized this in some sense a minimal way in the concept of a bicategory with a shadow. So maybe I should just put that here before I write it out for Hauschild homology. This makes sense anytime you have what's called a bicategory with a shadow. The bicategory is the structure that allows you to tensor things along lines, and the shadow is the extra operation that lets you close the line up to a circle. If you know about symmetric monoidal bicategories, then these provide examples of bicategories with shadow. The idea is that we strip away the extra axioms and we just focus on the axioms that let us do that. So now let me write this out again for Hauschild homology. So on one side, I have Hauschild homology of K, and my bimodule is K. And then I apply this co-evaluation map. Then I get Hauschild homology of K with coefficients in V dual tensor over R with V. You really should be thinking of this as a bar construction. When you think of it as a bar construction, there's this isomorphism that rotates it around. And now the K is on the inside. And then I can apply F. I'm going to leave a gap here. V tensor over K with V dual. And then I can apply evaluation and end up at Hauschild homology of R with coefficients in R. So that's what I do algebraically, but in pictures, I have colored chalk. That's what I have. So in pictures, I have a circle. You imagine this circle is labeled by K. If you like, I'm putting Ks everywhere. That's a way of thinking about the cyclic bar construction. And then I do this co-evaluation map. So that's sort of like...
Can you pick another color?
Yes. Yes. Thank you. Yeah, green might be brighter. Let's try green. Oh, yeah, that's much better, yeah? Okay, thanks. It's a little counterintuitive because the board is green, but... So I do this co-evaluation map. I then introduce this segment of the circle that's labeled by R. And at the endpoints of that segment, I have my V dual and my V. Like that. If you want to think of this in physicsy terms, it's like I've created a particle-antiparticle pair where there was nothing before. Yeah. All right, I know what this crowd likes. Good. So let's keep going. So the particle and the antiparticle spread out. At some point, I apply F to the particle, whatever that means. So they spread out, and then instead of thinking of this as a rotation, I'll switch focus from focusing on this side of the circle to focusing on this side. So I'll imagine that they've come all the way around like this, and now they're starting to approach each other again. So now there's my V dual and V. I'm trying to draw these carefully so that they line up. And then at the very end, I do an evaluation. So the particle and antiparticle collide, and now everything is surrounded by R. There we go. And of course, at some point I applied F as well. Somewhere in the middle here. Here's yet another way of visualizing this. This is a cylinder. And these are just levels of the cylinder. And the cylinder has a curve in it. The curve is on the back side, has that shape, and then it comes around to the front side, and then it's shaped like that. So that tip of the curve at the top is where you do co-evaluation, and that tip at the bottom is where you do evaluation. And then, maybe at some point here in the middle I apply F. Yeah. So that's the field theoretic way of thinking about this. This is sometimes called a two trace or a secondary trace. In that language, the primary trace is the one that creates the circle. It's the one that creates Hauschild homology. And then this is something that gives you a map from Hauschild homology of one thing to Hauschild homology of another. Okay. So that's the picture. So now let me just finish translating that picture back to the Reidemeister trace that I defined earlier. So while I'm erasing the board, I'll say, the point of having it in a picture like this is that this isn't just about rings and bimodules. This is about any setting where I can tensor things in a straight line or a circle. So I can do this for modules. I can do this for module spectra over ring spectra. I can also do this for parametrized spectra. Right? These are all settings in which you can make sense of these operations. And when the settings are equivalent, in particular modules over group rings versus parametrized spectra, you're getting essentially the same trace. So it gives you two different ways of writing down what is the same invariant. All right, I'll focus for simplicity on modules over rings because it's a little bit easier to get intuition for that operation. Okay, so let R be z pi. In other words, z pi 1 of my manifold. And let V be chains of the universal cover. So this will maybe remind you of Wolfgang's talk from yesterday. In fact, the fact that V is dualizable here is exactly the kind of duality that you were talking about. For instance, if M is aspherical and this is a Poincare duality group, right, then it's the dualizability of this as a module over this. There's the map I want to take the trace of. So the trace of that is the Reidemeister trace. Almost. There's a slight complication in that this is not linear. So I have to add a little correction term. So instead of getting a map from V to V, I get a map to V tensored with another bimodule. This bimodule is actually just the ring R again. So V ends up not changing. It's still the same abelian group. But I'm going to change the R action on this slightly. So I'm going to denote that by putting a little f here. The changed R action is if I have A act on the left on B and I have C act on the right, then, so the right action is the usual one, so I'll get BC. But the left action, F induces a ring homomorphism, and I apply that ring homomorphism first. So I add that twist. So that gives me a map up here. Let me pull this back down for a second. The complication that adds is that I have to add W in here. And down here, I get coefficients in W. So in my string diagram, when I apply F, let's say I apply F right here, then I get a little strand that pops off. And that strand is called W. So with that caveat now, the trace of this is the Reidemeister trace. This is how you conceptualize it. So this non-commutative trace of F, the map it induces on the universal cover. That's a map from the Hauschild homology of Z to the Hauschild homology of z pi with coefficients in z pi twisted. And that turns out to be just a z in degree 0, and that goes to, this turns out to be the zeroth homology of our old friends, the twisted free loop space. And there you go. That map is the Reidemeister trace. That's the alternative definition. Or that's the less geometric, more algebraic definition. Yep.
If my manifold was simply connected, I can forget about a lot of these decorations or...
Yeah, if the manifold is simply connected, then the Reidemeister trace contains the same information as the Lefschetz number. So in that case, you therefore get a converse to the Lefschetz fixed point theorem. That's one application of the Reidemeister trace, actually. Yeah. Right, so in that case, for connectivity reasons, this group ends up just being a z in degree 0. All right. So as I said, this recipe, it's general, it's formal. It's just this string diagram. So I can apply it in lots of different settings. One setting I can do is instead of rings, I can do ring spectra. So let's do that, because why not? So I can make this the suspension spectrum of base loops of M. I mean, after all, this was integers and loops up to homotopy. I mean, an integer is really a degree of a map between spheres. A loop up to homotopy, well, let's just take all loops. So this module gets replaced by exercise to think about why this should be the right answer. Replace this by the sphere spectrum with a trivial action of loop space on a point. And then this. So the tricky bit is about translating between HZ modules and chain complexes, but if you ignore that, then it's about if you extend scalars from base loops to that set of connected components, and you apply it to the point, you extend scalars, you're supposed to get the universal cover of M. So you can think about how that works. It's a nice exercise. So this is supposed to be a further lift of the dualizability of this over z pi. And since we have the sphere, maybe this is as far as you can lift it. So then W I also replaced by a suspension spectrum of loops M. And I also put a twist of the action. So loops M acts on one side and it acts on the other side. And I also twist that left action in the same way that I did before. So then, that gives me a map from the sphere spectrum into the topological Hauschild homology of this ring with coefficients in that bimodule. And that turns out to be the suspension spectrum of the twisted free loop space. So with the same recipe, you've turned it from an algebraic concept into a more topological one. You've put some more topology into it. Now, the nice thing about doing this, I mentioned earlier, you want to be able to generalize the Reidemeister trace to families. Once you can think about this using spectra, once you can think about it in this formal way, it becomes a lot easier to generalize it. So this gives you an invariant for families. So say I have a fiber bundle E mapping to B, and I have a fiber-wise self-map F. So in particular, on each fiber M, I get a self-map. Then I can think of that as a parametrized family of fixed-point problems. So in this setting, you get a fiber-wise version of the Reidemeister trace. Essentially, by using spectra that are parametrized over B, anytime over here you would have just used spectra. And then this is a map from the suspension spectrum of B to the suspension spectrum of the twisted free loop space. So for every point of B, I'm getting a stable homotopy class here, and it varies continuously over B. This is slightly a lie, because as I vary over B, the map F changes. So it's actually not quite this, but there's a parametrized spectrum over B whose fiber is this, and it's a section of that parametrized spectrum. So that's what it actually is. I'm writing it this way because it's a little easier to write on the board. So what's the corresponding version of Beckman's theorem? this is a result of Klein and Williams from 2007. It says that f is homotopic to something that's fixed point free across the family. So here I'm still assuming that I'm assuming still that M is a manifold, and so this is a fiber bundle whose fiber is a manifold. I think I want it to be smooth. I might not need that. But anyway, so let's be conservative and say smooth. So f is homotopic to something fixed point free across the family if and only if this vanishes in the homotopy category.
The dimension?
The dimension, yes, very important. So before, we needed the dimension of M to be at least 3. So what we need here is we need the dimension of B to be finite. So B is a finite dimensional cell complex. And then the dimension of M needs to be at least 3 plus the dimension of B.
So that's the dimension of the fibers, which are 3?
So if the base is 1-dimensional, the fibers need to be at least 4-dimensional. Yeah, so in particular, then the total space would be at least 5-dimensional if B is a manifold and the total space is a manifold. Yeah, so that's what the stable range looks like for this problem. Okay. So that's the story of fixed point theory. So this project with Kate, the goal of this project is to make this story run for periodic points. That's the goal. To take both this complete obstruction and generalize it to a complete obstruction for periodic points, and also these various conceptual ways that we have of interpreting it, to understand these periodic point invariants and what they're supposed to look like so you can see them across multiple settings as following the same recipe. So that's part 3. So I'm going to fix an integer n. N is at least 1. And I'm going to say by definition an n periodic point of f is a fixed point of f to the n. So you might squabble with me a little bit about this definition. When I say n periodic point, I actually mean a point whose periodicity divides n. So this includes the fixed points. This includes, if n is 4, it includes the 2 periodic points. And the question I want to focus on is the analog of the question I focused on for fixed point theory. So for a fixed n, can we remove these periodic points? Can we remove them by a homotopy? What is the invariant that governs this, and where does it naturally live?
But are you fixing now the n or not?
I'm fixing n for this. That's right. Letting n vary is more complicated.
Yeah.
Yeah. I'm going to fix n for this. Right. So the first thing you might say is, well, this is the same as a fixed point of f to the n, so clearly I should be looking at the Reidemeister trace of f to the n. And that is an obstruction, but it's not a complete obstruction. If it vanishes, I can modify f to the n to remove its fixed points. But that homotopy, there's no reason why it had to come from a homotopy of f. So it turns out this is not a complete obstruction, though it is an obstruction. If you think a little bit more, well, removing the n periodic points in particular means removing the k periodic points. So I should also be looking at anytime k divides n. That's convention for this talk. K always divides n. So therefore, the Reidemeister trace of f to the k for k dividing n, well, that's also an obstruction. Now, this actually is a complete obstruction. So that's the good news about this. This is a complete obstruction. This is a result of Jezierski. from 2001. So that's the good news about this. This gives us an indication of how we should think about periodic points. The bad news is that it seems like it's not a complete obstruction when we pass to families. So if I have a family, if I have a fiber bundle and a fiber-wise self-map, I can take the fiber-wise versions of the Reidemeister trace for all these k dividing n. And we almost had a counterexample. We don't quite at the moment, but it really seems like these are not a complete obstruction when you're in the families case. There's something extra that they're missing.
Remember that the case determines the other one. There must be a system, right? They must be linked.
They are connected. There are congruences between them.
But that doesn't suffice to. Yes, so we now write down an invariant for k for all this, and they are linked because the one for k determines the one for n, and then you get a system of compatibility conditions. But maybe it's.
Well, so the results I'm going to talk about is about how they're linked, but it's a little bit. It's not quite about going from some of these to others. It's more about there's a class in TR, and its image under a ghost map is recovering all these. I'm giving away the punchline. Okay. All right. Right, so this is great, but this is probably not true for families. We have a good reason to believe that it's not true. And, you know, we will not stop. We will not rest until we find the invariant that also works for families. That's our goal here. We're topologists. We want to find that invariant that generalizes. And so that's the question. It's an open question. What is the complete invariant for families? That's one of the motivating questions behind this project. So at the very least, since these work when I don't have a family, whatever we look at should generalize this. It should capture the same information as these and possibly more. So we have to find an invariant that's stronger than these. Okay. Well, we didn't start from scratch. Klein and Williams provided us with a candidate. Okay. So in fact, so this is fun. So more elementary constructions. I'm going to start with my map F again, and I'm going to construct the following map. It goes from a Cartesian product of n copies of my manifold to itself. And this map is called psi n of F. So it's very simple. I take an n tuple, x1 through xn, and I apply f to all of them. And then I rotate them by one click. So f of xn comes first, then f of x1, then f of x2. So that's what I do. This is called the Fuller construction. It was defined in a paper in the 1950s by Fuller. So if you stare at this for a little bit, we can make a couple of observations. First observation is that the fixed points, what does it mean for a tuple to be fixed by psi n f? There's a bijection between those and the n periodic points of f. If I have a tuple that's fixed, that means that x1 is equal to f of xn, x2 is equal to f of x1, x3 is equal to f of x2, and so on. So I have a n periodic orbit. And then I can just take the first point in that orbit. That's an n periodic point. So that's the first observation. This is somehow transforming a periodic point problem into a fixed point problem. But it's also an equivariant fixed point problem. So the other observation is psi n f is Cn equivariant. Here Cn refers to the cyclic group of order n, and it acts on that by rotating the factors around. So this is an equivariant map. And I'm trying to figure out what happens to the periodic points. Maybe I should stop that for a little while and think about this map and think about removing the fixed points in an equivariant way. That's not the same problem, but it feels kind of similar, so maybe the invariant that solves one might also solve the other. Well, what's the invariant that solves the equivariant fixed point problem? It's the Reidemeister trace. So I'll take the Reidemeister trace of psi n f. That's an element in the stable homotopy of the suspension spectrum of this. So this is free loops of m to the n, and it's twisted by this map. I mentioned that the Reidemeister trace is very formal. You can do it in a lot of different settings, and it always follows the same pattern. So we can make use of the fact that this isn't just a space, but it's a space that has the action by this finite group. When I define the Reidemeister trace, therefore, I can work not just with spectra, but I can work with genuinely equivariant spectra. And so I'm going to do that. And that'll give me a map, that'll give me a class in the Cn, well, this is in pi naught, in the Cn fixed pi naught homotopy group of that. In other words, concretely, a map from a high-dimensional representation sphere into a suspension of this by a representation. So that's the kind of thing that I can get. I'm going to call this invariant the Fuller trace. So that's the candidate. Let me leave that picture up. Okay. So, some conjectures that we were thinking about before. So, the first two of these are due to Klein and Williams. So, one is that this Fuller trace should somehow be recovering these Reidemeister traces of f to the k for k dividing n. If this has a shot of being the complete obstruction, it should at least be as powerful as the more straightforward, obvious thing, the more straightforward, obvious obstructions that I might define first. So that's the first thing you want to know. The second thing they wanted to know, and maybe I'll leave this vague, that the Fuller trace lives in TR. I'll explain what I mean by that in a second. And then the third, and I'm not entirely sure if this is something that they conjectured, but it's certainly the natural thing to conjecture, is that if you know, especially this first thing, that this Fuller trace should be the complete obstruction. So conjecturally, the Fuller trace is a complete obstruction to removing n periodic points in a certain stable range.
But also two is a conjecture, it's not known so far. Two is a conjecture, it's not known.
Two was a conjecture. 3 still is. So, very good. So we get to actually state a theorem in this talk. Okay, so this addresses the first two. And the third one is the subject of future work. But as I said, this sets up the road for number 3. It tells us that the Fuller trace actually is stronger than the Reidemeister traces of f to the k. So now let me state this precisely. So the Fuller trace, R of psi n f, here it is. This is a map from sphere into Cn fixed points of this twisted free loop space. So again, if you like, it's an equivariant map from a representation sphere into a representation sphere smashed with that space. I can forget the group actions. That gives me a map from a sphere into a sphere smashed with this space. And then after I do that, it turns out there's an equivalence. Free loops of m to the n, twisted by this map, are equivalent to free loops of m, twisted by the map f to the n. That's an equivalence of spaces, not just a spectra. So the theorem is that along that equivalence, the Fuller trace unwinds and becomes the Reidemeister trace of f to the n. So in other words, this is a stable homotopy class that has some symmetry. It respects some group action. If you forget the symmetry, then it unfurls, it unwinds, and it becomes this simpler fixed point invariant. This is somehow really the Reidemeister trace of f to the n, but with extra equivariant structure on it. So the second part is that there's this map R. This is where the restriction comes in. That goes to the same term, except I replace all these n's by k's. So if you like, I have an equivariant map from a sphere into a suspension, and then I take both sides and I restrict to the fixed points for some subgroup of the cyclic group of order n. Points that are fixed by the subgroup of order n divided by k. And so there's this residual action by the group of order k. So that's what I mean when I say this restriction map. So the second part is that when you do that, you get the Fuller trace again, only for k instead of n. So the Fuller trace has this self-similarity. And when you restrict to its fixed points, you get a smaller Fuller trace. And now putting that all together, let me combine these into one. There's R of fk. So indeed, this trace, this invariant, is this little bundle that contains inside of it these simpler invariants you had before. But they're packaged up in this particular way. It's just a class in the spectrum. And in fact, right, so this addresses 1. This also addresses 2. So what I mean by TR is the inverse limit of these restriction maps over positive integers and divisibility. So because when I restrict the Fuller trace, I get the Fuller trace, I can put these together, and I get an infinite Fuller trace in the inverse limit of these restriction maps. So that's the slogan that this particular periodic point invariant, this lives in TR. And that limiting class, you have to be careful when you state this. It's an obstruction to, if it vanishes, right? It vanishes if you can remove the n periodic points for arbitrarily high n. That's not the same as removing all the periodic points of all periodicities. Right? But in that precise sense, it's governing what happens to periodic points for all values of n.
Is there any lim 1, or is that unique?
This is up to lim 1s. Yeah. It turns out, though, that this class is really coming from something in endomorphism K-theory. And so you can, there is a canonical choice of what the lift is supposed to be. But for the purposes of this talk, let me just ignore the lim 1s. And when I say it's an obstruction, I'll do that modulo the lim 1s. Okay, so that's how these periodic point invariants are related. So in the last little bit of the talk, this is a joke, but in the last little bit of the talk, I want to show you a little bit of the proof. I want to at least give you some of the intuition behind why this is true. So the caveat is that because this is not the full proof, the other parts involve thinking about geometric fixed points for parametrized spectra, and they involve thinking about coherence theorems. So I'm going to draw some pictures, and one picture is going to be isomorphic to another picture, but it becomes quite tricky once you write things down carefully, making the isomorphisms match up, and guaranteeing that when I go from one to another, there isn't some slippage where I get two isomorphisms that are actually not the same. But let's ignore that. Let's draw the picture. Okay, right. So the Fuller trace, let's try to draw a picture of that mirrors the picture up here. So it's going to look different because my module is, well, my ring is suspension spectrum of loops of this. So that's actually a smash product. That's an n-fold smash product of suspension spectrum of loops m. If you like, it's a Hill-Hopkins-Ravenel equivariant norm of that ring. And my module is also going to be an n-fold tensor product of modules. So when I draw this picture, I should not be drawing one circle, I should be drawing n nested circles to represent that tensor product. Okay, so I'll just draw a little slice of that. So this is supposed to be a picture of R of psi n f. Okay, here's my picture. So I'm going to have n nested circles. If you like, this is a circle labeled by a tensor product of n copies of the ground ring. And then I'll create my particle-antiparticle pair. And that will be, my V is really a tensor product of 3 copies of E. So in each of these 3 circles, I'm getting a little segment like that. So now that's a tensor product of n copies of E. And in the middle here, I'm getting a tensor product of n copies of R. Okay, then I bring them around. When I apply this map, something funny happens though, because there's a shuffling. I shuffle the tensor factors around. So in my picture, I'm going to represent that by adding a braid to this loop. Like that. Let's see if I can draw this. I forgot to make that green. That's green, that's brown. That part's green. Let's make another green part, be efficient. And go through one more time, like that. That's after applying the map. And then I evaluate, and now I just get this braid. This loop with a braid in it. I mean, I'm actually in a symmetric monoidal setting, not a braided setting, so this is just for illustration. Okay, so that's what my trace looks like. Well, this is the ground ring, so actually, I have this braid down here. It's actually harmless to put the same braid up here. That won't change what map I get, so let's do that. There we go, that's better. So now look at that picture, and, well, this isn't n circles at all. This is one circle winding around n times. So really, I should take this definition of the trace, you might imagine this is on a cylinder, and I should lift it to the n-fold cover of that cylinder. So let's lift to the n-fold cover. So now I'm going to get just one circle, and it's just going to be labeled by k's everywhere, because that's my one circle winding around n times. And then when I do co-evaluation, let me do it this way, so I have my green circle. When I do co-evaluation, I'm going to get n evenly spaced co-evaluation maps along the circle, like that. And so now here, this is really going to be just V dual and V. So this is really just K, not a tensor product of K's, and this is really just R, not a tensor product of R's. And then they grow, let me forget about W for now, so they grow, I apply F, and then this V collides with that V dual, this V collides with that V dual, this V collides with that V dual. So they grow. Like that. And then they collide. So there's my unwound picture. The intuition is that this trace, this is equivariant. I can alternatively describe it this way.
Where is F in the picture? Where is F in the picture?
So F is applied right when these particles move past this twist. That's when I apply F. So at this point, I've moved the particles if you like. So remember when I applied F earlier, it also created this extra bimodule W. You can imagine that in this situation, I have the tensor product of W's here, but also this twist. And that altogether is the bimodule that I create when I move past this segment. So then over here, I would have n equally spaced copies of W. Does that? Yeah? Okay. Great.
Wanting to wrap up soon. There's no break.
Yes. Oh, okay. So let me just draw the cylinder and be done. So now you just put this on a cylinder. There's your 3 copies of F. And then, now that you have this description, you just move this curve by an isotopy that corresponds to applying triangle identities. There you go. All right, thanks.
Time for a couple of quick questions.
Yeah, sorry about that. Yep.
You mentioned already endomorphism of K theory, probably you've thought about this.
Mm-hmm.
You can dress up the oldest stuff, K naught of endomorphism of rings, and you get a map from there to there. Very nicely explained how this classical stuff can be lifted to spectra. Can you do the same on the K-sphere level? And then you get a cyclotomic trace from the K-sphere level to TC, and then you get your invariant from that?
So we're definitely thinking about that.
Yeah.
So, I mean, there certainly a lot has been said about traces on K-theory for spectra. But yeah, so we're thinking about what's known and what we can do for K-theory of endomorphisms in this setting. And this trace map, that should go maybe not to TC, but to TR, to this inverse limit of ours. Because, yeah, there should be a class up there. I mean, F is an endomorphism, so there should be a class up there corresponding to F, whose image is, and there is previous work saying under the ghost map it's hitting these. But so, in light of this, it should say, when I go to TR, I should be hitting this Fuller trace.
Let's start with coefficients, right?
Yes,
That's why
it's like the W theory of Lindenstrauss-McCarthy. Yeah,
So you don't expect a cyclotomic.
that's right. That's right.
Here and move on to the next topic.